Let's talk 1.2, problem solving with patterns. In this section, we're going to go ahead and see if I have some list, pictures, figures. Can I look at it, notice some patterns, and then work from there? So let's go ahead and start with what we've actually already been doing from the previous section. So let's see what happens whenever we work with an ordered list of numbers. Well, we actually have a special name for this. Here I have an example of an ordered list of numbers, 5, 14, 27, 44, 65. I call it an ordered list because, well, I have a group of numbers and they're ordered in this particular format. We actually call this a sequence. So, whenever I look at a sequence like what I have here, the first term is 5, the second term is 14, 27 is a third, so on and so on. Each one is separated by a comma, and individually, we call these the terms of my sequence. Specifically, we can identify the nth term of the sequence. So, for example, the first term, like I said earlier, was the 5. And I would write the notation a sub n for my nth term. Or in the case of my example, I can say a1 or a sub 1 is 5 because it's the first term of my sequence. Similarly, I can say A3, the third term, is 27. So we have a sequence. And in the previous section for 1.1, we actually described some patterns and made predictions. So those were really nice examples before, but what if I work with something a little bit more complicated? We know that my patterns are not always so cut and clear. So to handle this, I can go ahead and consider a difference table. A difference table? Well, it's a table that illustrates the differences from one term to the next. So it's kind of in the name, difference table. It's a table that uses the difference. And we can actually use this difference table to help me predict the next value or term, excuse me, in the sequence. So let's look at what we have here for example 1. Use a difference table to predict the next term in the sequence. And here I have them nice and spaced out, just so that we have enough room. I have 1, comma 7, comma 17, comma 31, 49, 71. And I want to figure out what's going on next after 71. So what we're going to do for this difference table is I am quite literally going to see what's the difference from one number to the next. From the beginning, 1 to 7. How do I go from 1 to 7? Well, I had to add 6. What about 7 to 17? I'm going to do plus 10. 17 to 31. I have 14. It's a difference. 31 to 49. I have plus 18. 49 to 71. I have plus 22. And I don't know what's going to happen next here. You might actually already be able to see a pattern, but let's keep on going and expanding our difference table. So if I look at my next row or my next sequence, I have 6, 10, 14, 18, 22, and some other mystery value. Let's take the difference again. How do I go from positive 6 to positive 10? Well, I would say there's a difference of 4. Well, from 10 to 14? Well, there's also a plus 4. And as it so happens, I have plus 4 over and over again. At this point, I'm noticing a pretty clear pattern. On this bottom row, it looks like I'm having all plus fours. So what's probably going to happen right here? Well, I'm going to take a wild guess and say it's also going to be plus 4 to get the next number after 22. Well, to get to the next number after 22, 22 plus 4, we have plus 26. So what I'm doing is I'm going off this last sort of column. All right, and then to finish it up, let's see, 71 plus 26, if I want to follow my pattern. 71 plus 26, I get what, 97 is going to be my prediction. So what I just did here is an example of a difference table. I kept on looking at the differences until I recognized a pretty nice pattern. Now I didn't need this third row on the bottom, but it kind of helped me solidify what I was doing was sort of in line with what our final answer will be. It helped me identify, yes, I for sure do have a pattern here. All right, so we have example one. We just drew a difference table, and I was able to determine and predict what's the next term in my sequence. Let's do another one real quick with example two. If you want to pause the video real quick and attempt it yourself, I highly recommend it. But if your hands are full, you can go ahead and continue watching. I have 5, 17, 25, 59, 89, 145. Once again, I'm going to go ahead and find the difference between these values. Let's start with 5 to 17. What's the difference between 5 to 17? I'm going to say we had to do plus 12. What about from 17 to 25? Well, 17 to 25, it looks like we're going to do plus 8. 25 to 59, we get a nice, let's see, 34. Yes, 34. I'm going to do the same thing. 59 to 89, we get plus 30. 89 to 145, we get, let's see, 56. I don't know what's going on here yet. I don't really recognize a pattern so far. We have 12, 8, 34, 30, 56. A little bit weird, but let's keep on going and seeing if we can recognize a pattern eventually. So, how do I go from 12 to 8, the difference? Well, to go from 12 to 8, we have minus 4. It's actually our first time we're using a minus, actually, for this difference table. What about 8 to 34? 8 to 34, we have plus 26. 34 to 30. I have a difference of negative 4. 30 to 56, it looks like plus 26. And I'm looking at this bottom row and thinking, well, I've got some sort of pattern here. I see minus 4 plus 26, minus 4 plus 26. So can you take a stab and see what's probably going to go into this blank? Well, if I were to take a guess and following the pattern I see on the bottom, I would guess this would be a minus 4. If I go up and continue, 56 minus 4, we end up with 52, plus 52 to be exact. And let's go back up again. What's 145 plus 52? Let's see, 145 plus 52, we should be getting 197. Oops, 197. So that's going to be my prediction for the next term in this sequence. So in this example, we definitely had a much more complicated looking sequence, but thanks to our difference table, we're actually able to identify the pattern with a little bit of work here and there. So that finishes our example 2. And actually, we're going to continue working with examples for a good rest of this section. We're just going to jump example into an example. So let's go ahead and look at example 3. Let's move on from our difference table, and let's focus on that nth term definition. Recall that the nth term describes the term in my sequence. So the third term would be, well, not much to it, but the third term. So given this formula for the nth term, give me the first 3 terms. And to be clear, let's start with n is equal to 1 of the following sequences. So in other words, I want to figure out if I have this formula, can I get a1 A2, and A3. So all we're doing for A1, for example, is we're plugging in 1 for n. So instead of n squared, what if I have 1 squared plus 1? Let's see, 1 squared, we get 1 plus 1, carrying it over, giving me 2. A2, and then actually let me write this on the side. A1 is 1. And I want A1, A2, A3. So what's A2? A2, I do pretty much the same thing. Instead of n, I'm going to plug in 2. 2 squared, we get 4 plus 1, or 5. And then A3, we get 3 squared plus 1, or 9 plus 1, giving me 10. Giving me the first 3 terms of my sequence, 1, 5, 10. Or if you want to write it, you can write 1, 5, 10 with commas in between. So we've got the nth term, first 3 terms of the sequence, if I have the formula. So really I'm asking, can you plug in 1, can you plug in 2, and can you plug in 3? Let's do a part B to really solidify this. Part B. Now I have something that's a little bit more complicated, but I think we can handle it. Again, I want A1, A2, A3, the standard business. I'm going to write them on the side here for my final answer. A1, let's plug in 1. 1 times 2 times 1 plus 1, all over 2. Ooh, lots of parentheses. On the inside, I have 1. Oh, sorry, on the outside, excuse me. 2 times 1, we get 2 plus 1 over 2, which gives me 3 over 2 for my first value. A2, I'm going to go through these a little bit quick because they're largely calculation, but feel free to take a pause to catch up as needed. I'm plugging in 2 for n. I get, let's see, 2 times 4 plus 1 over 2, or 2 times 5 over 2. But also my 2's cancel out, leaving me with a nice 5. And then let's do it for 3. 2 times 3 plus 1 over 2. Oops, my mistake. Let me finish that. That should definitely be a 3 up front. You'll have to excuse me. So let's see, we get 3. What's 2 times 3? 6 plus 1 all over 2. 6 plus 1, we get 7 over 2. And then 3 times 7, we get 21 over 2, which unfortunately doesn't really reduce down. So now I have 3 new terms in my sequence. Again, notice here, not again, notice here that my terms don't need to be whole numbers. I could have easily gotten fractions. So in this example 3, we worked with the nth term, and then we computed the first 3 terms of the sequence. So here I worked with the nth term. In the earlier examples, we worked with a list of numbers. Let's work with some pictures. Maybe if you're a little bit lost right now, maybe some pictures might help. So example 4. Let's say I look at this here. Consider the nth term formula for the number of tiles in the nth term of the sequence. And I have this picture. So my question is going to be, well, how do I deal with this? Determine the nth term form. Sorry, I'm just rereading that. Look at this picture and can you predict what's going to be happening? If I want the nth term formula, it might be helpful for me to predict what's happening for A6. Well, first thing I'm noticing is my picture is definitely getting larger as I proceed through here. I'm getting more tiles. In A1, I only had 1 tile. In A2, I had, let's see, 1, 2, 3, 4, 5 tiles. A3, I've got 9 plus 2, 11 tiles. A4, it looks like I've got 19 tiles. And then A5, it looks like I've got, let's say, 29. I did some quick math counting here. So for A6, can I make a prediction about what the picture is gonna look like next? Well, this might be a little bit difficult. Can you notice a pattern between these as I increase? Well, if I were to break this down, A1 looks a little bit weird. So let's start with A2. I'm noticing this 2 by 2 box and then this extra box on the top. So a 2 by 2 plus 1. Well, for this A3, I'm noticing a 3 by 3 box plus 2. For A4, I'm noticing a 4 by 4 box plus 3. For A5, I'm noticing a 5 by 5 box plus 4. So if I write it out like this, you might notice the pattern. For A6, you may be guessing that I'm going to end up with a 6 by 6 box. Let's see if I can draw this nicely. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So a 6 by 6 box. Oops, let me rewrite that. And then an additional 2, 3, 4, 5, 5 up above. So it looks like I sort of have this pattern here. So how do I write this as an nth term formula? Well, if I did this, I can do it for A7, A8, A9, so on and so on. What I'm noticing here is that it appears that I start off with a base of a box that is n by n. So for example, for A2, we saw here, we had a 2 by 2 box. And then for A3, we had a 3 by 3 box. 4 by 4. A4, we had a 4 by 4. Oops, you got to excuse me. I accidentally moved that. We had a 4 by 4 box. A5, we had a 5 by 5. A6, we had a 6 by 6. So it looks like in general, for the nth term, I would have an n by n box. So I start off with an is equal to n times n for that big portion. What about this little top? I'm going to call it a chimney on the top right. Well, here I had 1, 2, 3, 4, 5. If I notice, it was always 1 less than my n value. So that tells me, in general, I'm probably having n minus 1 added to my total. So if I were to write this out, I'm predicting an is n squared plus n minus 1. So here I'm using actually some of my inductive reasoning skills to make my prediction and turn this into an nth term formula. So quite a bit of work, but it may be a little bit of a new skill, but if you're really great with pattern recognition, you might be doing quite well here. So this was part A. Let's move on to part B, and you probably saw part C earlier. Part B says, how many tiles are in the 10th figure of the sequence? Well, another way I can read this is, what's A10? Well, remember, I had my formula earlier. I said an was n squared plus n minus 1. If that's true, and I want A10, I can just plug in 10 for n. That is, instead of n, I might have 10 squared plus 10 minus 1. Let's do some quick math. 10 squared, we get 100 plus 10 minus 1. 100 plus 10, we get 110. Minus 1, we get 109. So for part B, I'm predicting if I drew it all the way out to A10, I'd be drawing 109 boxes. So I'm definitely glad I don't have to draw that. Now let's look at part C. Actually, let me erase this so that I have my formula still up. For part C, and our last part for this lecture, which figure will consist of exactly 419 tiles? This one's a little bit different because instead of asking what's A10, A11, or AN, it's saying, well, when does it actually equal to 419? That is, I'm writing 419 is equal to AN. What's N? Well, fortunately for us, we know what A sub N is. It's N squared plus N minus 1. Now I'm going to rewrite that over here just so that I have the space. N squared plus N minus 1 is equal to 419. So let's see how can we solve this. We're going to do some algebra. I'm going to subtract 419 from the left and the right, giving me N squared plus N negative 1 minus 419. What do we get? Well, we get actually a nice value of negative 420. Depending on how you want to solve this, there's quite a bit of ways that you can solve it. Let's see, how do I make up negative 420? So if we think about it, let's see. We can probably break this down into, I'm running out of space here. N minus 21, N minus 20 equal to 0, giving us N minus, let's see, plus 20, excuse me. Oops, I actually reversed that one more time. N plus 21, N minus 20. Give me N plus 21 is equal to 0, and then N minus 20 is equal to 0. On the left, we end up with, sorry if this is trudging to the bottom, N is equal to negative 21, and N is equal to 20. So we have two values of N, but we know our N value has to be positive, meaning I should just have a final answer of N is equal to 20. In other words, after drawing this figure all the way up to A20, I should end up with exactly 419 tiles. So one thing that you might have actually noticed whenever I was going through these is that here was example 5, but if you're following along with me in my provided notes, you might notice that I actually skipped through example 4. So for example 4, if you're going to go ahead and try to attempt that problem, it's some really good practice. But besides that, I'll see you for the next lecture.